Alright class, this is going to be part 2 of our video on chapter 6, and this part is going to cover correlation. And before I get to correlation, I missed one slide on the previous part, and I want to go over it because it is pretty important. It says identify these having a positive, a negative, or no association. So it's important to be able to look at two variables and be able to tell if they would have a positive, a negative, or no association just based on logic. Let's look at heights of mothers and heights of their adult daughters. Genetically, the heights of the mothers, as that goes up, the heights of the adult daughters will probably go up as well. So one goes up, the other goes up. That is a positive association. What about the age of the car in years and its current value? So the control is the age of the car, and as the age of the car goes up, the current value is going to go down, so that has a negative association. The weight of a person and the calories consumed. The calories the control, because eating the calories will change this, the weight of the person. So the calories consumed goes up, the weight of the person goes up. That is positive. What about the height of the person and a person's birth month? I mean, as your birth month goes up, no, this doesn't make any sense. There's no association there. Your birth month does not have anything to do with your height. Like, as your birth month goes up, your height doesn't go up or down or anything like that. The number of hours spent in safety training and the number of accidents that occur. As the number of hours spent in safety training goes up, the accidents would go down. So that has a negative association, negative. So I hope this kind of gives you a logical idea of how positive and negative associations will work. And I thought it was a good thing to cover, so I wanted to go back and cover it. All right, so let's start with correlation now. We've been talking about association. Now we're going to talk about correlation, which is a way to calculate the association of a linear regression. It's a linear relationship. It has to be linear to be able to calculate correlation. If we had to put a number on the strength, we would not want to depend on the units that we used. If we had to talk about how strong the correlation is, we don't want to use a unit. So they come up with an equation here called the correlation coefficient. And we're really not going to get into the formula much, especially in on level, except I want you to notice that it has to do with the z-scores. And z-scores are how, remember, that's basically how above or below you are compared to average. You know, 2 standard deviations below, a standard deviation above. So z-score actually comes into play here when you're trying to figure out correlation. It's interesting to think about that. The z-score does come into play, so the stuff from the previous chapter is involved here. We're just not going to get very deep into how the z-score is involved. You might do that in a higher level college class, but here we're just going to talk about how this is the strength of a linear relationship. It has to be linear to have a correlation score. You cannot have a correlation unless it is a linear relationship. And next they gave you wording to use for different coefficient scores, correlation scores. Correlation scores go from -1 to 1, with -1 meaning they're strongly negatively correlated. So like a -1 would look like this. The dots would go down and they'd be really tight like that. And strongly negatively correlated. A +1 would look like this with dots going up. And they're almost perfectly correlated. Well, at 1 they are perfectly correlated. It'd be like a straight line basically. And that's very strongly correlated, positive. So from 0.8 to 1 they call it strong. From 0.5 to 0.8 it's moderate. And 0 to 0.5 is considered a weak correlation that doesn't really show a whole lot. Over 0.5 is when a correlation becomes interesting and we think it actually has some sort of relationship involved. And I would use this chart right here. I would absolutely copy. So pause and copy that if you need to. Okay, so like for instance, if we had a student's heights and weights and the correlation was 0.644, that's a moderate correlation. Look up here, we had that would be a moderate. So there is a moderate correlation between height and weight of students. So that's what that would mean, is there's a moderate positive correlation. Moderate positive. Which means as heights go up, weights go up. And they have a moderate relationship to each other, a moderate correlation. So we say the correlation tells us there's a positive, moderate, and it's linear as well. If we found the correlation score, that implies that it's linear. Moderate, positive, linear correlation. We'd also like to see the scatter plot to see if there's any outliers or anything or any weird parts of the data. They didn't give us a scatter plot here, but it's a good thing to see to be able to tell that fourth part, which is any kind of, unusual things like outliers and such. Correlation conditions. In order to ever do a correlation, since it's measuring the strength of a linear association between two quantitative variables, you have to have both variables be quantitative, which means they're measurable numbers. And they have to have the straight enough condition. Let me show you what that means. It means that your plot has sort of a linear connection to it, like you could draw a line through the middle like that. And it looks linear. Let's see, those both look like a line, but if you had data like this, you can't get a correlation on it. And this is baking temperature and score. I'm guessing it's the score of how good the food was, because if you bake it at the right temperature, you're going to get high scores. If you're baking it at the wrong temperature, you're getting crappy food down here. But then if you overbake it, you're getting crappy food again. That's a different type of relationship, and it's not going to be in this chapter, where it goes up and then back down like that. So that is not a linear relationship, and it would not be in this chapter at all. So it needs to be straight enough, and you need to not have any outliers. You can't have like a nice clean plot like this and then have like one way out here. It's going to throw off your data to the point where it's really almost useless. It's pretty much useless data because of these. An outlier can mess it up really badly. So those are the three important things. It's got to be quantitative. It's got to be straight. Well, straight enough, as in you could draw a line through it like that. See, that's not super straight, but it's straight enough where I could draw a line through it. It makes sense. It's a little distance on both sides, but you can draw a line through it and it kind of makes sense. And no outliers, no crazy outliers or anything. Definitely no curvature like this. So to talk about each one, quantitative variables condition, it applies only to quantitative variables. Like you can't look at the correlation between the color of a car and how many accidents it gets in and do correlation on it. You can look into that, you can research it, but it doesn't involve correlation. You wouldn't be able to find a correlation between the two. So you can't apply correlation to categorical data, masquerading as quantitative data. So check that you know the variable's units and what they measure. So you need to know like what's being measured and how many units and what type of units they're using. Otherwise, you can't be for certain that it's a quantitative variable. You can't like check, zip code versus something, because that's not quantitative. It looks like a number, but it's not quantitative. The straight enough condition means, like we were talking about earlier, it has to be linear. And correlation measures only the strength of the linear association. It's going to be misleading if it's not linear. You only calculate it using the coefficient for linear data. You can only do this on linear data. And then you can't have any outliers because they distort the correlation dramatically. And they make otherwise small correlations look big, or they hide a large correlation. It can even give a otherwise positive association a negative correlation coefficient. Just that one piece can throw the data off so much that it's messing it up. So if you have like a huge outlier, this becomes very inaccurate and it's not very useful. When you see an outlier, it's often a good idea to report the correlations with and without the point. Or maybe even look into why that outlier is there and possibly discard that point. There could have been an error in the data, a misreading or something, or somebody, or if it was some sort of performance, somebody might have cheated, something like that. All right, the last concept in chapter 6 here is about correlation and causation. A lot of times when these things are strongly correlated, you'll think for certain that one causes the other, but that is not always the case. Correlation does not imply causation. Whenever we have a strong correlation, it's tempting to do that. It's tempting to think that one caused the other. Now, it might have, and it's usually decent evidence that it could have, but it can never prove it, causation. You need other evidence to be able to prove causation. And let me give you some examples of that. There could be a hidden variable that stands behind the relationship that determines by simultaneously affecting both of them, and this is called a lurking or extraneous variable. Now think of there is a correlation between sunscreen and skin cancer. People that use sunscreen usually have a higher chance of having skin cancer, but it's not causing it. The key component here is both of them have a lot of sun exposure. If you're using sunscreen, that means you're having a lot of sun exposure, which is what is causing the skin cancer. So without talking about the amount of sun exposure someone's getting, you're missing a big part of the equation here. As a matter of fact, if you use sunscreen versus not using it, your skin cancer goes down. But if you look at it with just sunscreen and just skin cancer, you might be led to believe that it makes it go up, and it doesn't. So sun exposure is causing this to be off. So you can't just go by correlation. I'll show you some other ones. I like this one here, ice cream sales versus drowning deaths. And this is a true stat. As ice cream sales go up, drowning deaths go up. And think about what would be the cause of that. Obviously, eating ice cream isn't causing you to drown and die. What's actually causing this is the heat, the summer heat. Because in the summer, more people buy ice cream. And also in the summer, more people drown because more people are out swimming. So there's a hidden variable, a lurking variable that's actually behind this correlation. So you need to know that when you're dealing with correlations. I give another example here. There's almost a perfect correlation between Methodist ministers in New England and the amount of Cuban rum imported into Boxton over the years. Does increasing the number of ministers cause people to drink more? You might be able to make an argument for that, but no, it doesn't. Sometimes it's just a coincidence that they're correlated. This wasn't a coincidence. There was a variable lurking behind it, but other times it's just a coincidence. Or maybe there's just something else going on in the background, but that just seems like a coincidence. There's a lot of them that are just coincidences, and that's what's causing it. All right, that is it for chapter 6, and that will be the end of these slides. Just go ahead and try that homework now, and you'll be done with chapter 6.